Now onto our physical properties discussion that should be familiar to you. That's our usual nice little list. We have 6 compounds that we've encountered that all have very similar molar masses, very, very different boiling points because butane and 1-butene, of course, non-polar molecules, just dispersion. Propanol and acetone, the aldehyde and the ketone, they have dipole-dipole, so therefore they have stronger forces holding those molecules together in the liquid than butane and 1-butene do, so their boiling points are higher. And then you get to, first of all, the alcohol, and then the equivalent molar mass to carboxylic acid, hydrogen bonding available there. Acetic acid, ethanoic acid higher than the propanol because, of course, this can also dimerize with itself, really giving you nice, tight intermolecular interactions. Now, if we think about amines of that same molar mass, propylamine has a molar mass of 59, and that's the primary amine. Now let's have a secondary amine in which instead of having a propyl group, we have an ethyl and a methyl, and then we have an equivalent tertiary amine in which we have 3 methyls. By the way, note these are all structural isomers of each other. Can't you imagine the fun isomer question that you know is coming up on the worksheet for these things? Anyway, looking at these, we would say, well, a primary amine, you've got nitrogen bonded to 2 hydrogens, it can do hydrogen bonding. Here we got a nitrogen bonded to 1 hydrogen, it can do hydrogen bonding. Poor little tertiary amine, all 3 groups are alkyl groups, so no hydrogen left, but you've got a electronegative nitrogen going to be sucking electron density from these 3 methyl groups, therefore it will have dipole-dipole. So what you would expect at first is you would expect these primary and secondary amines to have boiling points close to the hydrogen bonding alcohol and acetic acid, and the dipole-dipole to have similar boiling points to the carbonyl compounds. However, there is a significant difference here because of the electronegativity of oxygen versus that of nitrogen. On a 1-to-1 basis, assuming all other factors are equal, hydrogen bonds associated with nitrogen are weaker than hydrogen bonds associated with oxygen. So propylamine, even though it's got the potential to make 2 hydrogen bonds, much smaller boiling point than you would expect at about 50 degrees, still significantly bigger than you would expect than you see for the pure dispersion ones, but the effects of the hydrogen bonds really not as significant here with this propylamine. Some of that has to do with, of course, the fact you've got a 3-carbon chain here, but then so did you have in propanol. Propanol's got the oxygen involved hydrogen bonds, poor propylamine only the nitrogen weaker hydrogen bonds. And we see that again when you've just got 1 hydrogen bond available instead of 2 hydrogens for hydrogen bonding. The secondary amine has 34 degrees Celsius boiling point, so really low. I mean, lower than even these dipole-dipole ones. And then again, nitrogen less electronegative than oxygen, the dipole associated with the tertiary amine, smaller than the dipole associated with these carbonyl compounds, and its boiling point actually only just a teensy bit higher than if all you had was dispersion. So the weakness of the hydrogen bonds and the general less electronegativity would have been a better word to use there, of course, of the nitrogen means that while we see an effect associated with the boiling points, it's not nearly as notable as when we were looking at the effects of oxygens. However, you've still got hydrogen bonds. You've still got hydrogen bonding acceptor capability, even with the tertiary amines. So what you find is that amines are water soluble up to having 7 carbons. So therefore trimethylamine, soluble in water, not miscible, but soluble in water. Propylamine, soluble in water, and so on. So a quick note on the physical properties. You see the effects that we have noted up till now, but to a lesser extent.